Welcome to the Deep Dive, where we plunge into the latest research and unearth the most crucial insights, making complex topics not just understandable but, well, genuinely fascinating. Today we're venturing into a hidden battleground that underpins our entire digital existence, the world of cryptographic security. We're talking about algorithms like AES 256. These are just, technical terms. They are, in essence, the inviolable guardians of our digital lives. They're the digital locks on your emails, the vaults protecting your banking transactions, the shields around your smart devices, pretty much everything that keeps your personal data private and secure. Without them, our data isn't safe, period. Now, when we typically think about cyber threats, our minds often jump to sophisticated software hacks, right? Clever coding exploits or maybe brute force attacks trying to crack the math. But what if the threat isn't just in the code itself? What if the physical hardware that runs these algorithms is, like, inadvertently leaking secrets, revealing the keys to the kingdom without a single line of malicious code ever being injected? It's a much more subtle, kind of insidious form of attack.
That's precisely the problem we're going to illuminate in depth today. You see, even the strongest cryptographic algorithms, the ones mathematicians deem practically unbreakable by, sheer computational power, they become vulnerable the moment they're implemented on a physical device. Whether it's the tiny chip in your smart card, the processor in your smartphone, or a powerful server in a data center, these devices aren't silent. They leak information as a byproduct of their everyday operation. Think of it like a security guard humming a tune that subtly reveals the combination to the safe. Not because they meant to, but simply as an unconscious habit. These unintentional leakages are what we call side channel attacks, or SCAs.
Side channel attacks, okay.
And these side channels can manifest in various forms. Changes in the device's power consumption as it computes, the electromagnetic radiation it emits, or even subtle timing differences in its operations. For our deep dive today, we're zeroing in on power consumption. It's proven to be an incredibly potent and, frankly, widely exploited channel for attackers.
Okay, power consumption. But here's where it gets really interesting and maybe a bit unsettling. This isn't your grandfather's side channel attack, right? For years, these attacks needed immense statistical heavy lifting, collecting and analyzing thousands, maybe millions of power traces to find tiny correlations. Painstaking stuff. But now, the landscape has completely shifted. Machine learning, specifically deep learning, has supercharged these attacks, made them terrifyingly efficient. Imagine an attacker being able to learn a chunk of your crypto key from as little as one single power trace. One. That's not just a game changer. It feels like a whole new ballgame for hardware security.
Indeed, it really is. This new capability, dubbed Deep Learning Side Channel Attacks, or DLSCA, significantly increases the threat surface for, well, virtually all internet-connected devices, from the smallest IoT sensors in smart homes or factories right up to the most critical network infrastructure. Anything performing crypto ops is potentially exposed. It transforms what was once a, theoretically complex high-barrier attack into something much more practical, scalable even, for a determined adversary. It sort of democratizes a powerful weapon in the cyber attacker's arsenal.
Wow. Okay.
So our mission for this deep dive, then, is to unpack an innovative circuit-level countermeasure that directly addresses this advanced AI-driven threat. We're talking about something called current domain signature attenuation, or CDSA. This isn't about patching software or tweaking algorithms. No, it's about fundamentally securing the physical implementation of cryptography at its very core. It's about building a physical shield, basically, ensuring the integrity of our data in a future that's, well, increasingly defined by AI's dual capabilities for attack and, thankfully, for defense, too.
Right. So by the end of this, you'll not only understand the terrifying precision of DLSCA, but also why this research and this CDSA tech is such a massive leap forward. It sounds like a critical step towards truly robust digital protection, making sure those digital locks we rely on aren't undermined just by existing. Okay, let's dig in.
All right, let's unpack this concept of side channel attacks a bit more. Like you said, these aren't about breaking the math of the encryption, AES 256 itself. Still solid. Instead, these attacks exploit the unintended physical characteristics of a device during its operation. I like your analogy of listening to safe tumblers instead of guessing the combination. You're exploiting a flaw in the physical thing, not the abstract lock design.
Exactly. These physical characteristics, these side channels, are unintentional leakages. They give an attacker clues about the internal workings. As we touched upon, the most common ones are power consumption, electromagnetic radiation, and timing. For this deep dive and the specific research we're looking at, the big focus is power consumption. It's often the easiest to measure and, well, it carries a lot of information because pretty much every operation inside a chip draws power, right? And those draws fluctuate based on the data being processed. It's not uniform.
Makes sense.
Now, within power SCAs, it's really important to distinguish between two main categories. They represent very different threat levels. First, you have non-profiled attacks, things like differential power analysis, DPA, and correlational power analysis, CPA. Here, an adversary directly attacks the target device using fancy statistical methods. Trying to find patterns in power, use that link back to the key thing here. These usually need a lot of power traces, thousands, maybe millions sometimes. To find those statistically significant patterns that eventually reveal the key, it's like gathering thousands of blurry photos and using algorithms to sharpen the image. Effective, but data hungry.
Right, lots and lots of data needed.
Then you have profiling attacks, and these are, frankly, significantly more dangerous. This is where deep learning really shines. In a profiling attack, the attacker doesn't just go straight for the target initially, no. Instead, they first build what's called an offline template, or a really detailed model. How? They use an identical device to the one they ultimately want to attack. Think of it as a practice dummy, a golden sample they fully control. This is the profiling phase. During this time, the attacker has complete access. They can feed it known data, known keys, and meticulously watch the power traces. They collect a rich data set, each trace perfectly labeled with the key info or intermediate value that caused that specific power signature. It's like building a perfect fingerprint library.
Okay, so they learned everything on a clone first.
Exactly. And once this detailed model is built and trained on their controlled identical device, then they can use this sophisticated template to attack a similar target device. And here's the kicker. They can do it using far fewer traces. Sometimes, in the most advanced cases, maybe just one trace.
Just one. Wow.
Yeah. It dramatically increases the efficiency, the practicality, and honestly, the scary potency of the attack. It's like that assassin analogy. Practice for months on a dummy, perfect the move, then take down the real target with a single, precise action.
And this brings us right to the deep learning part, which, yeah, completely changes the game. This isn't just standard stats anymore. It's giving an AI, a deep neural network, the power to find incredibly subtle patterns, almost invisible patterns, patterns that humans or older methods would just miss entirely. It's like the AI has a super magnet for finding that needle in the haystack.
Precisely. Deep learning side channel attacks, DLSEA, use these sophisticated deep neural network models, DNNs, for these super effective profiling attacks. Let's walk through how it works conceptually, based on the research. For AES-256, an attacker typically trains a separate DNN model for each key byte. So imagine 16 little AI specialists, each focused on cracking one specific byte of the 16-byte key, working together.
16 separate AIs, one for each byte.
The process has two main phases. First, the training phase. This is the heavy lifting for the AI. Power traces are carefully collected from a test chip running AES-256. Now here's a key technique they use. A fixed plaintext, the data being encrypted stays the same, but they systematically vary the first key byte. So maybe the same message gets encrypted over and over, but each time with a slightly different first byte of the key. Each power trace they collect is then meticulously labeled with its corresponding key byte value. The DNN then, over many iterations, using thousands of these labeled traces, learns the incredibly intricate correlated leakage patterns, the link between that varying key byte and the tiny fluctuations in power use. It's basically learning the secret handshake or signature of each key byte in the power signal. This usually needs, as the paper says, a few thousands of traces to get a really good model.
So it learns the electrical fingerprint of each key byte.
Exactly. And once the DNN is trained, once it has this super sensitive model, we move to the attack phase, and this is where the threat becomes, well, chillingly clear. The trained DNN is then fed unseen power traces from a target device, usually using the same fixed plaintext as the training phase. The DNN, having learned those patterns, predicts the correct key byte with astonishing accuracy. And here's the crucial and frankly alarming point. A successful attack can become feasible with as low as a single trace.
Still shocks me every time I hear that one trace.
Yeah. A single observation of the device's power signature during one encryption could be enough to reveal part of the key, like having a master key that works first try.
So what does this all mean for us, for system builders, for regular users? It sounds like it just blows the threat surface wide open for pretty much any device using crypto. Your smart thermostat, government systems, everything. It makes it way easier for an attacker to compromise a device once they've done their homework on a similar one they can get their hands on. This turns side channel attacks from maybe a niche concern into a very real, very potent weapon, right? Especially for IoT devices out in the wild.
Absolutely. It's a profound shift. It makes these attacks much more practical, especially against devices deployed in, let's say, less physically secure environments. Think remote sensors, consumer electronics. This isn't just theoretical anymore. It's a rapidly evolving practical threat that needs addressing. So to really nail down how serious this DLSEA threat is, the researchers first did something crucial. They rigorously demonstrated how effective a DLSEA attack is on an unprotected AES-256 core, just a standard core. They fabricated it on a 65 nanometer CMOS test chip. That's a pretty common process for lots of embedded systems you see everywhere. This initial phase was vital. It gives us a clear, measurable baseline, the before picture of vulnerability. By showing how potent DLSEA is against an unhardened system, it really sets the stage for appreciating the countermeasure later. The research details the attack method meticulously, making it crystal clear how DLSEA works.
Okay, and let's talk about the attacker's weapon here. That fully connected deep neural network. For those of us not deep in machine learning, you might wonder, like, how is this AI actually built? How does it pick up those tiny power signals? It's not magic, right? It has a specific structure. Can you give us a sense of that architecture without, drowning us in techno speak?
Absolutely. The structure of the architecture is key. Conceptually, it starts with an input layer. In this case, it had 250 neurons. Each neuron corresponds directly to one of the 250 time samples they measured in each power trace. So you're feeding the raw power data, that little snapshot of the chip's energy use over time, straight into the network, like a tiny digital microphone listening to the chip's power hum.
Okay, 250 inputs, one for each time point in the trace.
Right. Then, following that, there are 3 hidden layers, each one packed with 1,000 neurons. These hidden layers are the brain, the computational engine. This is where the AI does the heavy lifting, extracting complex features, learning those intricate patterns from the raw input. Now, each of these layers uses several important components. We don't need to get lost in the weeds, but understanding their purpose is helpful. For instance, they use something called a ReLU activation function, rectified linear unit. Think of ReLU like a simple switch. Negative signal in, ignored. Positive signal passes through. This introduces nonlinearity that allows the network to learn complex, real-world patterns, not just simple straight lines. It lets the AI recognize a complex signature, not just a basic spike.
So it can learn more complicated shapes in the data.
Exactly. Then there's batch normalization. This helps stabilize and speed up the training. Imagine teaching a class. Some students learn fast, some slow. Batch norm is like quick coaching for everyone during training, keeping signals consistent, helping the whole network learn faster and more reliably. They also include a 20% dropout layer. Dropout is clever. It randomly swishes off some neurons during training. Why? To prevent overfitting. That means the network doesn't just memorize the training data like cramming for one test. It forces it to learn more general principles so it can solve new problems, like breaking a key from a new trace it hasn't seen. And finally, L2 regularization is applied. This also discourages overly complex models, makes the network more robust, less likely to be fooled by noise.
Okay, so multiple layers, nonlinearity, ways to train faster and avoid just memorizing.
Exactly. All these sophisticated parts work together so the network can pick out those faint key-dependent signals with the whispers of the secret key from all the background noise. The final stage is the output layer. This has 256 neurons, one for each possible key byte value, 0 to 255. It uses the softmax function. Softmax takes the outputs from the last hidden layer and turns them into probabilities. It predicts the most likely key byte from that single trace. Basically, it says, based on this power trace, I'm 98% sure the key byte is A5.
That level of detail, even simplified, really highlights the sophistication here. It's not just guessing. It's a highly tuned system designed to find those secrets. This is serious AI work being used for attack.
And like any ML model, performance really depends on tuning its hyperparameters. These are the settings the designer chooses, not learned from data, like knobs on an equalizer. The researchers carefully optimized these to get the most effective attack on the unprotected chip. Their analysis found the sweet spot: 3 hidden layers, 1,000 neurons each, and a learning rate of 0.001. This specific setup allowed the DNN to really lock onto even the faintest patterns in those unprotected AES traces. Maximum attack power.
So, the moment of truth for the unprotected chip. With this highly optimized attack model, what were the results? How bad was it?
The results were, well, pretty devastating for the unprotected core. The DNN model, after training, hit a training and validation accuracy over 99.9%, and it did that within just 10 epochs. An epoch is one full run through the training data. So very quickly, the AI was virtually perfect on the data it learned from.
Okay, near perfect on the training data. But what about new data?
That's the critical part. The test accuracy on unseen traces also hit around 99.9%. So even with data it had never encountered before, the model kept its near-perfect prediction power, and it achieved this using fewer than 5,000 training traces. Think about that compared to older methods needing maybe millions. This deep learning model got near-perfect results with orders of magnitude less training data. They used a confusion plot, too, which basically showed a near-perfect diagonal line, correct predictions, with only 1 out of 256 key byte values being misclassified. It was almost flawless.
Wow, that just demonstrates it beyond any doubt, doesn't it? Unprotected AES-256 is critically vulnerable to DLSCA. It's not theoretical, it's a proven, practical threat, which makes finding good countermeasures absolutely essential, like yesterday. It really feels like a wake-up call for hardware security.
Okay, so if the core problem is this leaky current signature that reveals the key and deep learning can sniff it out so easily, then the solution has to be making that signature disappear, right? Masking it somehow, flattening it out so the AI gets confused. Exactly right. That's the fundamental idea behind current domain signature attenuation, or CDSA. The main concept is to embed the crypto core, the AES-256 engine in this case, inside specialized CDSA hardware. And the whole goal of this hardware is to drastically suppress that correlated current signature, to make the power supply current drawn by the whole thing look almost constant, or at least totally unrelated to what the crypto core is doing with the secret key inside.
Okay, suppress the signature, hide the activity.
Precisely. And it connects to a fundamental principle. The minimum number of traces needed to disclose a secret key, the MTD, is inversely proportional to the square of the signal-to-noise ratio, the SNR. What CDSA does is aggressively reduce the SNR of that leakage signal right at the power supply pin by making the key-dependent signal so incredibly weak, burying it deep under the natural system noise, and crucially, without needing to inject extra noise, which can be inefficient. CDSA basically prevents the machine learning model from learning any useful patterns. Even with tons of traces, it's like trying to hear that whispered secret during a roaring rock concert. The signal might technically be there, but the noise just completely overwhelms it. The AI can't hear it, can't learn it.
That rock concert analogy really works. Okay, so this isn't just a simple filter. It sounds like a really sophisticated, maybe even elegant circuit design. How does it actually do that, achieve this signature attenuation so effectively? What are the key parts?
It really is some clever circuit engineering. The researchers focused on a few key components. At the heart of it is a digitally tunable cascode current source, CS. This component is designed with a very high output impedance. That means it strongly resists changes in the current flowing through it. Its main job is to power the AES core, providing a really stable, consistent average current. It effectively isolates the AES core from the external power supply, stopping those tiny key-related current changes from getting out.
High impedance current source.
Okay.
Like a gatekeeper for the current.
Sort of, yeah. And next to it, there's a smart bleed path. It uses a bypass PMOS transistor to ground. A small delta current leaks through this path, providing local negative feedback. This clever trick lets the system handle variations in the AES core's average current without needing a big, power-hungry shunt loop, which would be bulky and inefficient. This bleed path helps with analog regulation, letting the system adapt smoothly without revealing those changes externally.
So it handles the fluctuations internally.
Exactly. And to further stop key info leaking, the unit current of that cascode current source, about 94 microamps, is deliberately set higher than the typical key-dependent variation in the AES current, which is around 72 microamps. This might seem subtle, but it's a really important design choice. It ensures that any key-dependent info that might otherwise show up as a change in the average DC current just doesn't make it to the main supply. It gets absorbed or bled off internally. It's like having a constant loud hum that drowns out the secret whispers underneath.
Got it. Constant hum masks the whispers.
Then there's a slow digital switch mode control, SMC, LDO regulator, low dropout. This isn't meant to be fast. It's a low bandwidth loop. Its job is to track and regulate the average voltage across the AES core, keeping it in a safe range. Crucially, it's designed with a dead band of 50 millivolts. This means it mostly stays inactive during normal operation. It only steps in to make bigger adjustments if the voltage drifts too much. This stops it from creating new high-frequency leakage paths an attacker could exploit. It uses dynamic comparators to watch the voltage and a counter to gently adjust the current source when needed. Very controlled.
Okay, slow and steady voltage regulation doesn't interfere much.
Right. Now, what really makes CDSA different from traditional LDOs is its core philosophy. Its supply current does not track the AES current. Instead, the design allows a small voltage droop, maybe 30 to 50 millivolts, across the AES engine itself. This droop is carefully managed so it doesn't hurt the crypto core's performance at all, even if it costs a bit of power. The real magic is the high impedance of that cascode current source over 10 kiloohms. Super high. This impedance ensures that any current fluctuations at the external supply pin caused by the AES working inside are dramatically weakened or attenuated. The math gives an attenuation factor, AT, based on frequency, capacitance, and resistance. And for this design, it results in an incredible current attenuation of more than 350 times.
350 times weaker signal. That's huge.
It is. And to make it even more efficient, they did another clever thing. They biased the cascode current source in sub-threshold saturation. Sounds technical, but the result is amazing. It boosts that crucial output resistance by about 10 times compared to a simpler design. This genius move then lets them use 10 times less capacitance, CL, across the crypto engine. Only 150 picofarads needed. Why is that good? Big capacitors take up a lot of chip space and cost money. So they get the same incredible signature attenuation, but with a much smaller, more efficient physical footprint. It's really squeezing maximum security from minimal resources.
Wow, okay, that really does sound like a masterclass in circuit design. They've thought through everything down to the physics to create this like stealth cloak for the chip's power use.
And it's not just theory. They measured it extensively. They took time domain power traces from their actual test chips, comparing the unprotected AES with their CDSA protected version. The measurements dramatically showed the difference. They confirmed an actual measured signature attenuation of over 350 times for the CDSA AES 256 traces compared to the unprotected ones. So the empirical data backed up the design. The stealth cloak works as advertised.
That's fantastic validation.
Yeah. And they also did a thorough design space exploration, testing different CDSA settings to find the best balance of security and efficiency. They found the sweet spot was a 0.3 volt dropout voltage across the current source and a bleed size of 400. Just for context, that unprotected AES core baseline was running at 0.8 volts input, using about 1 milliamp average current at 50 millihertz. So they had clear comparisons. It's that kind of meticulous detail that really grounds this research.
All right, this really is the moment of truth, isn't it? We saw how devastating DLSCA was against the unprotected chip. We've gone through the ingenious CDSA design, promising to bury those power signatures deep under noise. Now, the ultimate test. You take that highly attenuated signal, where the key signature is supposedly invisible. Can the exact same deep learning attack, the one that cracked the unprotected AES 256 so easily, can it still find patterns? Can it still get the key?
And the answer, quite emphatically, is no. This is the absolute core breakthrough here. They took the captured power traces from the CDSA-protected AES 256 and fed them into the exact same 256 class DNN architecture, the one that got 99.9% accuracy before. And despite that DNN's proven power, it simply could not be trained on the protected traces. It learned nothing. And this wasn't for lack of trying. They really pushed it. They attempted to train the model with an astronomical 10 million traces. 10 million traces. Over 100 epochs, that's 100 full passes through all that data. Immense computational effort. Yet, despite all that, the training and validation accuracy showed zero improvement. Nothing. The AI was completely blind to the secret.
Just couldn't learn anything at all. Why? What was stopping it?
It's fundamental. The current signature of the AES operations just remained deeply buried under the system noise. And crucially, this was achieved without needing to inject extra artificial noise. It was the inherent property of the CDSA hardware itself. The key-dependent signal was, quite simply, effectively invisible to the AI no matter how many times it looked. Like trying to find that specific grain of sand on a vast beach, but you're wearing a blindfold and maybe earmuffs too. The signal just wasn't detectable for the AI.
Okay, so if the DNN couldn't learn anything useful, what did its output look like when they tested it, when they asked it to predict key bytes from the protected traces?
The results perfectly illustrated the complete failure. If you looked at the confusion matrix, that grid showing predictions versus actual values, it was basically random scatter. Instead of that clean diagonal line of correct guesses, you just saw predictions all over the place. Imagine every possible key byte value having an equal chance of being predicted, regardless of the real value. The test accuracy was incredibly low, hovering right around random chance. For 256 possibilities, that's about 0.39%.
Basically guessing.
Pure guessing. It unequivocally showed the DNN couldn't find any meaningful patterns in those highly attenuated traces. Total failure to extract the key. The AI, for all its power, was utterly baffled.
That is truly phenomenal. So let's translate this. What does it mean for real-world security? The numbers here must really tell the story.
They really do. Let's compare side by side. For the unprotected AES-256, the DNN needed less than 5,000 traces to train fully, get near 100% accuracy. And that efficient training enabled a devastating single-trace attack. One look could compromise a key byte. Now, for the CDSA AES-256, the DNN could not be trained at all, even when thrown 10 million traces. That's not just a small improvement. It translates to an absolutely astounding greater than 2,000 times improvement in DLSCA immunity. Imagine needing 2,000 times more data and effort just to start training an attack model. It basically makes the attack practically infeasible.
Over 2,000 times harder to attack. Wow.
And the researchers point out that measured 350x signature attenuation theoretically suggests even stronger protection. Specifically, it implies protection potentially up to over 350 squared times the signal power attenuation, which translates to immunity against attacks needing maybe over 600 million traces for training.
600 million traces.
Yeah. Now, they were time limited. They couldn't physically run tests with 600 million traces. The data volume is just insane. But they demonstrated resilience up to 10 million, and the underlying physics suggests the protection goes much, much further. The signal is just too deeply buried.
Okay, incredible security improvement.
Yeah.
But there's always a cost, right? What about overheads? Power, chip area.
Good question. Such a big security jump usually comes with trade-offs. The CDSA implementation did introduce a power overhead of 49.8% and an area overhead of 36.7% on the chip. Now, those aren't zero, obviously. You need to consider them for mass production, especially for tiny, ultra-low power IoT devices. But honestly, for such a massive security enhancement against such a potent threat, those overheads are remarkably low. When you think about the value of the data being protected, critical infrastructure, financial secrets, personal privacy, these costs often seem very reasonable. And here's the really crucial bit. There is zero performance degradation for the crypto engine itself.
No slowdown.
None. The AES-256 still encrypts data at full speed. Security isn't coming at the expense of functionality, which is often a major hurdle for countermeasures.
That is a massive win. And you mentioned this isn't just for AES-256. It's described as generic. So this isn't a one-off fix, but potentially a foundational technology for securing other crypto too. That sounds incredibly powerful.
Exactly. It's designed as a generic circuit-level technique. The principles of attenuating the current signature should apply equally well to other cryptographic algorithms or even other processing cores that might leak sensitive information through power consumption. That makes it a really versatile tool in the hardware security toolbox, providing a potential universal shield against this advanced class of DLSCA attacks. It's a big deal.
This brings up a really important point. People have tried to stop side-channel attacks before, right? This isn't the first attempt. So what makes CDSA stand out? Why did those older approaches kind of fall short when faced with these new AI-driven attacks? It feels like we've been playing defense for a while.
That's a crucial question, and it really puts CDSA's achievement in context. You're right, previous countermeasures definitely existed, and they offered decent protection against, let's say, traditional statistical SCAs, but they largely crumbled when facing the analytical power and adaptability of DLSCA. Take logical and architectural countermeasures, things like time domain obfuscation or adding clock jitter. The idea was to mess up the timing, make traces misaligned, harder to analyze, but these were often beaten by more advanced AI models, especially convolutional neural networks, CNNs. CNNs are incredibly good at finding patterns even when things are shifted around in time. They can essentially see through the timing randomness.
So the timing tricks didn't fool the AI?
Not the advanced ones, no. Yeah. Similarly, masking-based countermeasures. These try to randomize the intermediate values inside the crypto calculation. Again, shown to be pretty ineffective against sophisticated DLSCA. The AI, looking at subtle correlations across many dimensions, can often still figure out the unmasked secret. It's like trying to hide a pattern by throwing confetti on it. A powerful enough AI can still see the underlying design.
Okay, masking didn't hold up either. What about other circuit-level ideas?
Right. There were other circuit-level approaches closer to CDSA's philosophy. Things like charge recovery logic, switched capacitor current equalizers, integrated voltage regulators. These offered some protection against older SCAs, but they often came with serious downsides, like slowing down the crypto core, needing huge amounts of power or chip area because of large passive components like capacitors or inductors, Or sometimes they even introduce new leakage paths, like electromagnetic EM radiation from those big capacitors. But the absolute critical point for today's discussion, none of these previous circuit-level solutions had been rigorously tested against DLSCA attacks until the CDSA work. They simply hadn't faced the modern AI adversary. CDSA is effectively the first circuit-level technique that has explicitly demonstrated DLSCA resilience. It's been put through the AI gauntlet and came out on top. That's a major milestone.
That's a fantastic clarification. It really shows why this is groundbreaking. And just a quick technical point for listeners who might be curious.
Yeah.
You mentioned earlier the researchers used a fully connected DNN, not a CNN, which we often hear about for pattern recognition. Why that choice specifically?
Yeah, that's a good question. CNNs are often the go-to for things like image recognition or signals where patterns might shift around. But the key here was that the power traces they captured were perfectly aligned in time. They used on-chip trigger pulses to mark the end of each encryption precisely. So every trace started and ended at the exact same points relative to the operation. In that kind of synchronized scenario where the signal's timing is consistent, CNNs don't actually offer much advantage over a well-structured, fully connected DNN, especially when you're dealing with the very low signal-to-noise ratio that CDSA creates. A CNN's real strength is handling those time shifts or distortions. But if the traces are already aligned and the signal is almost gone anyway, that CNN advantage isn't really needed. The fully connected DNN was sufficient and effective.
Okay, so alignment made the simpler DNN structure effective.
Right. And it's also worth just quickly mentioning the assumption they made during profiling, using a fixed plaintext. Now, a real-world attacker might try varying the plaintext too to get more info. That's true. But using a fixed plaintext is a standard and robust way for researchers to quickly and clearly assess the inherent leakage of the device and, more importantly, to evaluate the countermeasure's effectiveness directly. It simplifies the experiment, letting them focus purely on whether CDSA hides the key-dependent signature itself without getting tangled in complex attack variations that would just need even more data and time. It proves a core defense concept.
Got it. Okay, so after this incredibly deep dive, let's bring it back to the listener. Whether you're securing a huge data center, designing a tiny secure IoT gadget, or just wanting to know your own personal data is safe when you use your phone, what's the practical takeaway from this groundbreaking research?
The so what is genuinely profound. It touches every part of our digital lives. This research delivers a concrete, hardware-level defense against this new wave of incredibly powerful, AI-driven cyber threats. It means the fundamental integrity of encryption can be better protected, right where it's most vulnerable, not in the abstract math, but on the physical chip where it runs. And this isn't just theory. It's a fabricated solution, proven to work in a common 65mm process. It paves the way for genuinely more secure devices across the board.
So more secure chips are possible now.
Yes. Think about the impact. For IoT devices, often out in the open, physically insecure, resource-constrained, CDSA offers a vital layer of protection against powerful, localized attacks. For cars, where security flaws can be life-threatening, this can harden critical control units. In healthcare, protecting sensitive patient data on medical devices. Even more crucial. For cloud servers, processing vast amounts of sensitive data. A new defense against attackers trying to grab keys directly from the silicon. And for your own phone, securing your payment keys, your private messages, better shielding against these advanced physical attacks.
It really covers a lot of ground.
It does. This technology helps ensure that the digital locks we depend on for, well, everything from national security to personal banking aren't undermined simply by the act of doing their job. It builds a stronger, more resilient foundation for digital trust in our hyper-connected and sometimes scary digital world. It's about securing the very bedrock of our digital society.
We have really gone on quite the journey today, haven't we? Started with the, frankly, terrifying precision of these deep learning side-channel attacks cracking keys with a single trace, and then explored the elegant, clever engineering of current domain signature attenuation, CDSA, seeing how it literally hides that secret power signature, making it invisible even to sophisticated AI.
Indeed. It's a fascinating arc. This work provides a practical, efficient, and importantly, generic circuit-level countermeasure. It's a solution that helps the physical reality of cryptography live up to its mathematical promise, instead of betraying it. This is a critical step forward, a significant win in that never-ending race between the attackers and the defenders. It reinforces our digital walls right where they were becoming worryingly thin due to AI attacks. It's not just about winning one battle, it's about strengthening the fundamental architecture of trust.
And it's fascinating how the incredible power of machine learning,
first used to expose these subtle hardware vulnerabilities,
Yeah.
is now being met head-on by equally ingenious hardware solutions that leverage a deep understanding of circuit physics, silicon fighting back against algorithms in a way.
It really is. And this raises a really important, maybe a provocative question for all of us to think about. As AI continues its relentless evolution, getting even better at finding ever more subtle patterns, maybe uncovering leakages we haven't even thought of yet, new timing channels, thermal signatures, who knows? How quickly can our hardware designers and security architects adapt? What other physical vulnerabilities might machine learning expose next? And how will we respond with the next generation of physical countermeasures? This intricate dance between attack and defense, it's far from over. The ingenuity required on both sides is only going to increase. It's a challenge that will keep security researchers, chip designers, AI experts busy for decades, constantly pushing the boundaries of what's possible and what's secure.